we will be discussing a dynamic model of growth given to us by Robert Solow. Let us start by talking about the supply side of the model. Output is represented as a function of capital and labor, so we can write y is equal to F KL. The Solow model is based on the assumption of constant returns to scale. So, when we increase both capital and labor by lambda, then the output also increases by lambda times. So now it is lambda y is equal to F lambda k, comma lambda L. Putting lambda is equal to 1 by L, we now can express the production function as y by L is equal to F k by L, comma L by L. Now, we write the production function in terms of lowercase letters, representing all the variables in terms of per worker. So, now y in terms of lowercase is equal to F k, comma 1. Since 1 is just a number, it does not affect the function. So the production function gets reduced to y is equal to Fk, all in lowercase letters. From now on, throughout the model, we will be talking about all the variable in terms of per worker, unless otherwise mentioned. Initially, we are also going to assume that population is constant. The production function assumed in the model represents diminishing marginal productivity of capital per worker, MPK. This is the reason why the production function becomes flatter as the amount of capital per worker increases. Now let us talk about the demand side of the model. Assuming a two-sector model, the demand for goods comes from consumption and investment. Using the National Income Account's identity, we express output per worker Y to be equal to consumption per worker C plus the investment per worker I. So, Y is equal to C plus I. The Solow model is based on the assumption that people save S proportion of their income and therefore consume 1 minus S proportion of their income. So, C is equal to 1 minus S Y. Now we can write the demand equation as Y is equal to C plus I. This in turn is equal to 1 minus S Y plus I. This implies I is equal to S Y, which in turn represents I is equal to S F K. This is the famous saving investment equality. What we have talked about so far tells us that the output per worker is given to us by the production function y is equal to Fk, and the saving rate allocates the output per worker between consumption and investment per worker. Since the output per worker y is dependent on the stock of capital per worker k, it is imperative on our part to discuss how the availability of k is determined. From our knowledge of basic macroeconomics, we know that the stock of capital increases if the gross investment is more than the depreciation expenditure to maintain the existing stock of capital. If gross investment is less than the depreciation expenditure, then the stock of capital actually falls. And if the two are the same, then the stock of capital does not change at all. In terms of symbol, delta K is equal to I minus del K, which in turn is equal to S Fk minus del K. When K is less than K star, for example K1, then the stock of capital increases as the gross investment is more than del K and we move towards K star. When K is more than K star, for example K2, then the stock of capital actually decreases and moves again towards K star as investment is not sufficient to maintain the stock of capital. If we are at K star, then the stock of capital remains at this level as investment is just sufficient to maintain the existing stock of capital. This is the stock of capital that we call the steady state stock of capital per worker. Since the output per worker depends on the capital stock per worker, the output per worker also remains constant at the steady state as the stock of capital per worker remains constant. However, if the saving rate increases, then the steady state stock of capital per worker also increases. This happens because the existing steady state stock of capital K1 star, now the gross investment is more than the depreciation expenditure needed, and as a result, additional capital is formed. Once we reach K2 star, the stock of capital continues to remain the same as the gross investment is now just equal to the depreciation expenditure needed to maintain the existing stock of capital per worker at this level. As the economy starts moving from the lower steady state K1 star to the higher steady state K2 star, the income per worker also starts growing from Y1 star to Y2 star. But once we reach K2 star, steady state stock of capital per worker, the growth of output per worker also stops. So, a change in saving rate affects the level of income and also leads to a temporary growth of income per worker. It effectively means we can achieve any level of stock of capital per worker as the steady state stock of capital and thereby also the associated level of income per worker by changing the saving rate. As we can have all the levels of stock of capital as the steady state one, we replace K by K star on the x-axis of all our diagrams from now on. So, by increasing the saving rate, we can increase the income per worker. Shall we, therefore, always try to increase the saving rate? The answer is no, because from the welfare point of view, it is the consumption per worker that is more important for an economy. That takes us to discuss what we call the golden rule level of capital, K gold star. It is that level of steady state stock of capital per worker that maximizes the consumption per worker rather than the income per worker. Going back to the national income accounts identity, Y is equal to C plus I, we get C is equal to Y minus I. Since we want to find out the steady state stock of capital per worker that maximizes the consumption per worker, we replace the equation by C star is equal to Fk star minus del K star. It is not difficult to find K gold star. If we increase the saving rate a little, that results into an increase in K star by 1 unit. The output per worker increases by an amount equal to what we call the marginal productivity of capital MPK, represented, of course, by the slope of the production function. However, the depreciation expenditure required for this additional unit of capital per worker also increases by an amount equal to del. Now, if the increase in income, MPK, is more than the increase in depreciation, del, then the rest of the income left after meeting the depreciation requirement leads to an increase in the consumption per worker. However, if MPK is less than del, then the consumption per worker falls as the additional income is not sufficient to meet the additional requirement for depreciation, and we have to meet it by cutting down on the consumption. So, as long as MPK is greater than del, we should try to increase the steady state stock of capital as it leads to an increase in the consumption per worker. However, if MPK is less than del, then we should try to actually reduce the steady state stock of capital to increase the consumption per worker. It effectively means that the golden rule level of capital K gold star takes place at the steady state level where MPK is equal to del. In terms of our diagram, the slope of the production function should be equal to the slope of the depreciation line. It is not difficult to understand that the basic Solow model with the assumption of fixed population cannot explain sustained economic growth. At any steady state, including the golden rule level, stock of capital and therefore income per worker is constant. If the number of worker is constant, then the absolute level of stock of capital should also be constant if the stock of capital per worker has to remain the same at steady state. For the same reason, the absolute level of income also has to remain constant at any steady state. To explain sustained growth of output, we must now introduce the population growth. Let us now assume that the population and the workforce grow at a constant rate n. This increase in the size of the workforce leads to a fall in the stock of capital per worker even if the gross investment is sufficient to maintain the absolute stock of capital. So, if the per worker stock of capital has to remain the same, then the gross investment has to cater not only to the need of depreciation but also to the population growth. This is to say that the investment has to be equal to del plus n into k if the economy has to be at the steady state. Del k amount of investment is needed to maintain the existing stock of capital and nk amount of investment is needed to provide capital to the additional workers joining the labor pool, and this leads to the formation of additional stock of capital at the rate n. So now the absolute stock of capital and therefore the output grow at the rate n. However, output per worker y is equal to uppercase Y divided by uppercase L remains the same, as both uppercase Y and uppercase L are growing at the same rate n. So, we have been able to explain now the sustained growth of absolute level of output by introducing the population growth. The introduction of population growth also changes the condition for having the golden rule level of capital for maximum consumption per worker. Now, out of the additional output MPK, when we have one more unit of capital per worker, del amount has to be spent to maintain the additional unit of capital, and n amount has to be spent on giving one unit of capital to the additional workers so as to maintain the stock of capital per worker at the new level. So, if MPK is greater than del plus n, then the consumption per worker increases, and when MPK is less than del plus n, then the consumption per worker decreases. One can therefore safely say that the consumption per worker will be the maximum at that level of steady state stock of capital per worker where MPK is equal to del plus n. This is the new condition for golden rule level of capital. As we saw earlier, that though the introduction of population growth explains the growth of output, over a period of time. It does not help us in explaining the sustained growth of standard of living, as it fails to explain the increase in output per worker. It brings us to the next source of economic development, and that is technological progress. We now assume that through technological progress, the efficiency of worker increases at rate g. To achieve technological progress, we need to invest in capital. We are talking about labor augmenting improvement in technology, in the sense that this acts as if the size of labor force is increasing. So, N plus G represents the growth of effective worker. So, to maintain the stock of capital and the efficiency of worker growing at the rate G, when the population grows at the rate N, we need to invest del plus N plus G into K to remain at steady state. This tells us that the absolute stock of capital in this case will increase by N plus G rate. As a result, the total output will also increase at N plus G rate. Since the population is growing at the rate N only, the extra rate of growth of output G leads to an increase in the income per worker, and therefore the standard of living also increases at the rate G, as the two are related. So, it is the technological progress that explains the sustained rate of growth of standard of living. The golden rule level of capital condition also gets modified. When we increase the level of capital per effective worker by 1 unit, the output increases by NPK. In order to maintain the steady state stock of capital per effective worker at the new level, we need an increased investment equal to del plus N plus G. So, if MPK is greater than del plus N plus G, then it leads to an increase in the consumption per effective worker. In this case, we should try to increase the saving rate. If MPK is less than del plus N plus G, then it lowers the consumption. It effectively means the maximum consumption per effective worker is when MPK is equal to del plus N plus G. To conclude the Solow model, we can say that the growth of an economy depends on accumulation of capital, population growth, and technological progress.